Good afternoon. Do you hear me? Good afternoon, everyone. Then today, right now, you're supposed to have pre-lab report of this lab, recrystallization lab. Because pre-lab, the purpose of the pre-lab is to serve you prepared for doing the lab actually. Okay, so whatever lab you do, you have to write pre-lab report before the class time. Then during and after class time, you are writing post-lab report. So right now, you should have a pre-lab report for the recrystallization, and during and after today's class, you have to write post-lab report. Bam. Okay, watch carefully. Let me enlarge this thing. Okay, so the video is from MIT. It's been, I think, more than 15 years or something. Yeah, but you know, the technique is about the same. The outside
Recrystallization. A large percentage of a chemist's time in the laboratory is spent purifying chemicals. Learning to use a variety of different purification techniques efficiently and effectively is key to becoming a successful experimentalist. Recrystallization is one powerful method for the purification of crystalline solids. This video will outline the purification of naphthalene by recrystallization. The technique of recrystallization involves 5 main steps. First, an appropriate solvent is determined. Recrystallizations can be carried out using either one or a mixture of 2 solvents, depending on the solubility of the sample. Next, the sample is dissolved in a minimal amount of the proper hot solvent. At this point, the solution can be decolorized and insoluble contaminants can be removed by performing a hot filtration. The resulting solution is then cooled to induce crystallization. And finally, the purified crystals are collected by filtration, washed, and dried. This video will first outline the general procedure for carrying out a one-solvent recrystallization of naphthalene, followed.
So, let's move back a bit.
Are collected by filtration.
So these steps, okay, let's memorize now. First, choose right solvent, whatever that means. It will be clear soon, okay? Choose right, and then let me finish. Then dissolve the sample in that chosen solvent. Can you imagine now? Okay, you chose the solvent using some principle of chemistry you will learn today, and then you dissolve them completely in a way, very important manner. Then you decolorize and do hot filtration. Actually, this step is optional, okay? So far what? First, choose the solvent, right? And then you dissolve. Optionally, step 3, you decolorize, then hot filtration. Oops. Step 4, then you cool down to get the crystal again. Recrystallization is taking place in this step 4. Then you got the crystal, so you gotta collect and filter, then wash it to clean up a bit. Okay, let's okay guys, pretend I'm right in front of you. Tell me the 5 steps. Just pretend. Number 1, yeah, Number two, using that. Mm-hmm. Yes. Yeah, you're right. Then three, optional, but if you have a color or some other impurity not dissolved yet, then you do this, right? Hmm. Then the main process, step four. Yeah, you're right. Absolutely. And finally, yes, you got it. Okay, 5 steps. You have to memorize. Let's go. Now they're showing you to choose right solvent. Let's see. Someone's screaming, help, help. So let's see. Oh, there was a my silly action. Somebody's mocking me, huh? Okay, let's go. There are tip, couple of different methods. In our school, we only do one solvent, system, but it's good to know how in other places like MIT, Columbia, what they do. Okay.
Carrying out a one-solvent recrystallization of naphthalene, followed by instructions for adapting the procedure to a two-solvent recrystallization. Choosing an appropriate solvent for a recrystallization is a very important step. You won't get acceptable results if you don't pick carefully. It is helpful to have a variety of solvents at your disposal. If solubility data for your compounds has been published, this will help you to narrow the range of potential candidates. Once you have decided on a few prime contenders, you will perform solubility tests to find the ideal choice. You will need a hot water bath for the solubility test as well as the recrystallization.
Caution! Organic solvents are flammable. Never heat over an open flame.
Meaning Bunsen burner is not proper way of heating things in organic lab. Okay? Any video showing Bunsen burner as organic lab, you know, they don't know what they're doing. Don't listen to them. Whatever they teach, ignore. Um, so in our lab, we have a high-tech hot plate. Yet, you're not allowed to have a flammable solvent near the hot plate. Without flame, organic solvent can catch fire over flash point. So flash point is where the temperature with just the presence of oxygen give enough of a kinetic energy for organic compound vibrate vigorously enough to break the bond, get into the radical chain reaction with the oxygen, and create explosion and even flame. Okay, flash point for organic compounds are not that high. Therefore, I mean, we also use time to time with the distillations and other experiment, the surface of the hot plate easily going over 300 degrees Celsius. That's enough for most of the organic compound catch fire without flame. So that's one of the safety issue you need to remember. This will be on the test. Safety is a prime goal of this class. If you forget everything about organic chemistry, at least you need to remember in the chem lab, I need to behave this way, not behave that way. Okay, this is one of them. Don't put flammable organic near the hot or heat source. Okay?
To set up a water bath, place a large crystallizing dish about half full with water on a hot plate. Add some boiling stones and turn on the heat. Don't turn it up all the way. Start halfway and adjust from there.
The purpose of the boiling stone, yes, of course, it is going to heat up the whole water in the flask evenly too. But more than that, it is showing us very evident phenomenon like bubblings and some disturbance or even the stones jumping up and down as water boils. So we know that this thing is hot. Okay, safety. Without boiling chips, boiling stones, water's gonna boil very well. You know that size of the pot. You boil it every day to cook, right? It is going to boil so well. We made the thing clear, transparent, so we can see things, so we can get more safe environment. That's the purpose of it. Okay, so the boiling chip on the test. The purpose of the boiling chip, most of the time, the answer is to give even boiling. That's not wrong, but you are missing one of the major things. Okay, to show boiling more clearly.
To perform a solubility test, place approximately 20 milligrams of your compound in a test tube. Add a half of a milliliter of.
Did you memorize how many milligram? You'll have to memorize milliliter as well. Then you know the percentage for solubility test. Okay? Whatever you do in the future, if someone says a solubility test of solid, then you should remember this number.
Add a half of a milliliter of the appropriate solvent and swirl. Wait a couple of minutes and then make note of your compound in a test tube. Start halfway and adjust from there. To perform a solubility test, place approximately 20 milligrams of your compound in a test tube. Add a half of a milliliter of the appropriate solvent and swirl. Wait a couple of minutes and then make note of whether or not the compound dissolves. For example, at room temperature, naphthalene is insoluble in ethanol and water, but soluble in toluene and acetone. If there is still solid remaining, clamp the tube and heat it in the water bath until the solvent boils.
So again, during the practical test or other lab classes we do together, if I watch you holding these test tubes with a bare hand and with the gloves even, right? That's not the proper way. You gotta have some sort of clamp, or whatever, heat, heat insulating tool. This thing get pretty hot because you are boiling things, and the vapor means vapor reach the boiling point, right? So vapor from this liquid will have a dead boiling point reaching up here where you're going to be holding it. And vapor is going to escape, and if this touches your hand while you're holding, you're going to feel like, oh, so hot, and you drop it. And then it's organic liquid, and it's going to have a contact with a hot plate down there, and it's going to be boom. You think I'm making all this up, but this is something that I have watched movie as a safety training since grad school. Okay, that actually happens. So I'm gonna make a deduction. If I see some improper, unprofessional conduct of experiment, not just running, not wearing goggles, not only those things. Speaking of goggle and lab coat, if you don't bring, I'll send you back home to get it. Then you're gonna miss some portion of the lab. I don't mind. Okay, that's the lesson. That much your safety is more put ahead of education, and that's the education. So don't forget, next in-person lab, bringing the lab coat and the goggle. If not, you'll send home back. The chemistry department will not lend those things, and it's not safe if people share things from renting.
Swirl the tube and make note of whether or not the compound dissolves. After heating, naphthalene is still insoluble in water,
Yeah, you see the bottom? You have still solid. Whether it's less than before or not, it's not completely soluble.
But it is now soluble in hot ethanol. Now that you have finished the solubility test, how do you decide which solvent to use for your recrystallization? The ideal solvent is one in which your compound is insoluble at room temperature, but soluble at the boiling point.
Okay, let's memorize. There were 5 steps for this experiment. First step, you check solubility. There are 2 stages, right? Okay, some of you, please type. What are the 2 stages of finding solubility? Just giving you idea, near the grading season, right after exam or something, people who participate actively will get some benefit, obviously. Yeah, how do you choose right solvent? There are 2 stages. Yeah, it should be not soluble at room temperature. That's what we're looking for. Okay, if something's soluble at the room temperature, that solvent is not good solvent. Then among the solvents that doesn't dissolve your impure solid sample at room temperature, you are going to heat up. That's the second stage. After heating, while they're boiling, the boiling solvent, whichever it is, able to dissolve it from the chosen one, right? From the first stage at room temperature testing. Among those things, chosen ones, if anything dissolving at the boiling, you have to make sure they're boiling, then that's the best one. Say none of the chosen ones are dissolving at the boiling point, but I see one dissolves better than the other. This is more detail, okay? Not completely dissolving, none of them at boiling at the second stage from the chosen solvent from the step 1. But then you are looking for better dissolving one. At least you can choose the best one. Maybe not ideal. You can choose best one. Then we have to dissolve anyway in the later stage of the experiment, right? Then what are you going to do? Easily, you can add more solvent to dissolve more crystal. As far as it dissolves, at least partially, right? You can add more solvent. Common sense. Okay? You understand. Go ahead. Okay, so that's raising almost every year interesting point, right? Important point I have to address because every year's issue. Students saying the textbook procedures are not same as ours. And then the professor is always going like, so what? I mean, it's different. So what? So the thing is this, when you cook pasta, right? When you cook pasta, when you cook in your kitchen, when you do it in grandma's kitchen, and you go to other friend's house for party, you cook there, for example. Do you cook same way with the same equipment, with the same ingredients? Not really, right? You cook pasta anyway. You know what it means. Once you master the technique, doesn't matter what they give, you can cook pasta. That's the beauty of science. Science is to not to memorize as it is. I told you that, right? First day. This course, organic chemistry, is not history class. The beauty of or purpose of this real science course starting from this and afterwards when you take upper level science courses, please don't take it wrong. The purpose of the professor teaching you is not making you remember things, making you apply, welcoming some variations, get excited about new things, new ingredients, new perspectives, new equipment. You're still able to adopt those different things and adapt. Okay? So our procedure, book procedure, YouTube procedure from Professor A, Professor B, Professor C, they're all different. What the heck they're doing, right? They are doing same thing. You learned one way of cooking, then you're able to, if you really understand, you can cook in any other places, in any other with the other ingredients. Because it's unknown sample, you are purifying. Okay? Unknown is unknown. You don't know what that is. You cannot follow procedure written in the textbook. That mindset is a Gen Chem mindset. Now you are a real scientist. So please open your heart. Embrace these things. These are beautiful stuff.
Remember, at room temperature, naphthalene was soluble in both toluene and acetone, so neither of these will work. After heating, naphthalene remained insoluble in water, even at the boiling point. This means that ethanol is the solvent of choice. It dissolves the sample at its boiling point, but not at room temperature. Now that we have decided on a solvent, it is time to dissolve the sample in some hot ethanol. Get ready by heating some ethanol in the water.
Notice that even large amount, not the testing amount, 0.2 milligram, right? You put grams of sample in the bigger flask. The name of this flask, Erlenmeyer flask. Erlenmeyer is one of the alchemists. He was not a real chemist, but he made up this equipment. Okay, so we still give the name, the alchemist Erlenmeyer, for this equipment. This person's using this arm clamp, holding it to put it in the boiling water. Also, she doesn't put the flask right on top of the hot plate because it's going to boil. Boil means evaporation. That means gas comes out. Gas is heavier than air, so it will drop on the hot plate, catch fire, kaboom. Not good, right? So you're going to have water. Water is going to give a maximum 100 degrees Celsius. So this solvent will boil, but not as vigorously as you put on the hot plate. Also, you have this amount of the empty space. So even some gas escape and come down, you have an empty space, slowing down the vapors touching the hot plate. And some of them will gonna evaporate into the air rather than flowing down. So much safer. Okay? You are sensing that is asking you to visualize invisible stuff. That's what science is, right? Science is all about microscopic stuff, controlling macro scale stuff. You need to build this keen eye that allows you to imagine and see clearly and predict their behavior in the micro world. I ask you to imagine that. That's the main purpose of this course.
Water bath. Remember to add some boiling stones and clamp the flask securely so that it doesn't tip over. Place the sample in an Erlenmeyer flask, but before adding solvent, it is a good idea to set aside a small crystal. It may come in handy later if you have trouble getting crystals to form.
So you have to remember these details. People who know this technique will understand why. That's why you need to remember this. The 5 steps are simple. Now you see the details. You are doing second step, dissolving things. Dissolving doesn't take place at room temperature, so you have to set up the hot plate and boiling bath, water bath. Then before you actually dissolve, you have to save a little. Not many people save sample at the practical test. Then there goes deduction. If you actually know the technique, you have to save it. Okay? Some Korean ramen, when they cook, you have to save some liquid. Otherwise, yeah, you're not gonna get proper outcome. If you ever, you know how to cook ramen, you will save some. Same thing. You have to save a little bit of impure crystal before you dissolve everything. So step two, still step two we are doing.
When dissolving your sample, use a minimal amount of hot solvent. This will ensure good recovery of crystals in the end.
Look at the use of the
Add
pipette.
hot solvent in small amounts, swirling and heating in between each addition until the sample just dissolves.
She did not completely dissolve, all right?
Caution. If it won't dissolve, it's probably an impurity.
So the reason they give this warning is because when you try to dissolve this already, still not dissolve the crystal with the amount of the liquid they add. In order to dissolve it, you have to put more and more liquid, the hot liquid to it. You're not adding at once. The book says add 10 milliliters of water to this acetonitrile or something. That's because they've done this. But we are not training you guys in order to do only repeat the same experiment, right? We are training you to work in the environment, scientific environment, like a hospital, for example. You deal with a new disease, new virus, new, I don't know, new patient with a new stuff. So you gotta, have this flexibility and application mindset. Anyway, so you are adding new hot solvent into this to dissolve it, as we talked about. But we have to use a minimum amount of solvent. It's not going to be 10 milliliter all the time. It depends. So how do you know? As soon as you dissolve everything here, that's when you stop adding. And that can be 10 milliliter. Sometimes it can be 1 milliliter, honestly speaking. So no one knows. Only known things textbook says add this. Doesn't mean you always add that amount. Trust me, on the practical exam, people actually add the 10 milliliter at once because the book says so. That's a memorization. You add little by little until you boil while it is still boiling. Okay? But the warning is this, more detailed technique. You notice as you add 1 pipette full of a hot liquid to the mixture of solid, you actually see some amount of solid disappear because you have a more liquid that's boiling. And that's your choice, right? And you are keep adding and you have to check. It's keep disappearing. But some point you add it, it looks like it doesn't disappear. And you add more, I still have a solid. And I still have a solid. If you don't check every time whether it is actually taking away some solid, then you are adding too much liquid. Why? The thing is not dissolving now. That thing can be maybe impurity. Now because of the impurity, you did not check whether it's dissolving. You ended up having too much liquid. Then it's a problem for step 4. Thus, it is a big problem for overall experiment outcome. You have to check. You may laugh, but people chat, people talk. Don't look at this guy, look at their eyes and talking while they're doing this. That's not right manner in the lab. So inhumane? Yes, maybe. That's why scientists have a no joking or sense of, humor, maybe. At least in the lab. So you need to learn that inhumane behavior in the lab, at least. You gotta check, give your best attention to this baby right here. This can save millions of lives by killing bacteria, a virus. Okay? And then as soon as you sense like, okay, this addition is not dissolved, then you have to give additional real good attention to next addition. Yeah, it doesn't really go away. Then stop. That is your impurity, and it could be even your boiling stone or glass chips. They used to replace in these days instead of boiling chips, they use glasses. Anyway,
Caution. If it won't dissolve, it's probably an impurity.
so it won't dissolve means after some point, right? It will keep dissolving, but it doesn't dissolve anymore. That moment, that's a missing in this warning sign. That's why I have to stop and tell you this practical aspect of lesson. These practical things will be more on the test than theory. You should know that. This is a lab course. I'm going to ask questions such as things like, in the step 2 of the recrystallization, and you don't know what the step 2, then you're in trouble, right? If you knew, okay, why would you have to stop adding liquid? Then why would you stop adding liquid, huh? Maybe because it's all dissolved? Yeah, maybe that too. But then you are only telling me half of the answer. So you get 5 out of 10. The other half is when the solid is not anymore dissolving. Not only completely dissolved, okay? Also when it's not dissolving anymore. You need to give me 2 answers. Then you get 10 out of 10. You gotta remember these things. This is a real science.
Now that the sample is in solution, impurities can be removed through decoloration and hot filtration.
So I told you this is optional, all right? You dissolve everything and your solution is giving color. Then you have a step 3 need to be done in 2 stages. Stage A, decoloration. Stage B comes, that's hot filtration. It's filtering, but there are many filter methods I told you, right? So this is one of the filtration techniques when you need to filter when it's hot.
Take a close look at the solution. Is it the right color? For example, if you're expecting white crystals and your solution is yellow, then there is a soluble impurity. One easy way to remove small amounts of colored impurities is with activated charcoal. Before adding any charcoal, cool your solution to slightly below the boiling point.
Caution. Adding charcoal to a boiling solution will cause it to boil over.
Add a
Okay, so what it means is 2 things I need to say. When you cool down below boiling point, it means you're not putting this thing in the ice bath. Okay, just below, slightly below boiling point. Just sees the boiling, but it's still hot. It must be still hot. Don't put it in the cold water bath or ice bath. The solution is still hot. Why? Let's see anybody were following me well. I'll give you +1 extra point for your first exam. Okay, first the two right answers. Two people. Why you cannot, you shouldn't, you must not cool down too much at this point. Your first exam is only 20 points or something, okay? 1 point is not trivial. My camera is ready to take a picture of right answer. Anybody? Don't be shy. It doesn't have to be right. Try, give it a try. If you are listening to me so far, this solution is the solution that you dissolved your mixture solid in 2 stages, right? When it's cold, it wasn't dissolving. When it's hot, it was able to be dissolved. Now you have a color and you need to add this charcoal to remove color, reduce the solution's temperature. Why? Okay? Type it. Type on the screen. You want to have a crystal formed? That's what you mean? I kind of see answer, but I don't see it clearly. So, do you want to have a crystal formed? That's why you want to cool down? On the test, if the answer is not clear, I cannot give a point, right? But here I have 4 acceptable answer because it's a first date, today. Not 2 people. I'll give these 4 people extra point. So the extra point chance is over. Let's keep going. The answer is yes, you're right. We want the crystal to be dissolved, right? But we were only able to dissolve when it's hot. When it's cold, when we choose the solvent, right? When it's cold, the qualification for the good solvent was not able to dissolve at cold. So if you cool down, it won't be able to be dissolved. It'll come out. That's not what we want. We want the compound to be dissolved and stay that way until we finish. So that's why you don't want to cool down too much in the ice bath or cold water. But because the temperature is still high, what happens is the evaporation of the liquid taking place, vigorously. So these little vapors are rising and escaping. So there is a wind blowing from the bottom, okay, out of the openings. And these charcoals are more lighter than the cooking powder, flour, okay? It flies so easily with a, even vigorous breathing, these things can fly. And that thing is a toxic in a sense. So when you try to put this thing into this, openings, because of the, draft, the wind from the bottom, the the charcoal's gonna, just scattered into the water, and that's dangerous. That's why we need to cool down a bit. I told you it should not be cooled in the ice bath. Okay? It should not. Just under. Okay, so at least a few of you were following me seriously. I will remember your names. Okay, I'll remember your names. Now, um, he will explain hopefully. Let's see.
Small amount of charcoal to absorb the impurity. Do not add too much or the charcoal will also absorb your compound.
Hmm. Yeah, that's exactly what I was gonna say. The charcoal has a big surface area with a good interaction with any compound. Okay, they don't have a brain, they don't have a sensor. They don't know whether that molecule is colored impurity or the main compound you want to preserve. They don't know. They just take it. Because the colored impurity is in the less amount than the major compound, we put a little bit of a powder, charcoal, then the charcoal is gonna randomly absorb colored molecule impurity, right? And then the main compound as well. You anyway lose some compound by doing this, but you only need a little bit because your impurity of the colored is a little bit. So you add just a bit, although you may lose a little bit of a main compound. In return, you get more pure compound. But make sure you do this quickly because the solution's getting chilled, okay? You don't want that. You want that to be hot. Then you have to move quick. It's very delicate. Not too hot, not too cold, and quick enough. Not too much, not too little. These things are called know-hows, techniques you are learning. So I am pinpointing where you need to pay attention. Are you making note right now? This is a serious class. You're not just listening to me like watching TV, right? I'm not a showman. Color pens and everything. Make a note. These points you need to remember. The best thing is actually doing it, but unfortunately, we're not doing it. So you have to give your brain some practical electric signal in the proper place, not the frontal brain.
Swirl the flask and boil it in the water bath for 2 to 3 minutes.
So once the charcoal is in the solution, it's not going to fly, so you can boil again.
Charcoal is very fine and can be hard to remove by filtration. It is easiest to add a small amount of a filtering agent, such as sea light, to absorb the charcoal and facilitate the filtration.
Zeolite is basically a powder of the clean rock. You grind them up, hours and hours grinding with some equipment. I cannot explain simply, but yeah. And they are very active. The surface is reactive. So it is going to react with preferably charcoal because the charcoal is a high surface material. And then at the moment when she was shaking it, charcoal had some attachment of the impurity and some main compound. As you connect the charcoals with these zeolite particles, you're actually clumping up the unnecessary chemicals as well. Okay, but they are clumping up due to the zeolite reacting with the charcoal. You are now easily able to remove the impurity along with the charcoal and the zeolite. Remember these things. How do you remove colored material? Charcoal. That's not enough, okay? That's a simple memorization. You gotta put some description, the principle. Charcoal using that nonpolar surface, high surface area, have a London force with the colored compound, and as well as our main compound. Then zeolite is making chemical bond with the charcoal and making the size of the charcoal grain bigger and bigger. That makes easier for solid filter off by porous filter paper. You gotta have some scientific principle, not like charcoal, zeolite. That's not gonna get more than 5 points out of 10 from your exam.
Add only a small amount, swirl the flask, and heat it once again for 2 to 3 minutes before performing a hot filtration. If the solution is colorless, the decoloration step is unnecessary. but you still need to look carefully for any undissolved solid in the flask. If you find any, it can be removed by performing a hot gravity filtration with fluted.
Okay, so we are doing step 3, right? But this is optional, but because of the color we had, we need to do it. Stage A of the step 3 was decolorization. Now you have the decolored solution plus colored material on the surface of the charcoal, but the charcoal is considered as an impurity, so you have to remove them. When you have a heterogeneous solution right now, right, liquid and the solid, it's easy. Filter. We don't use a suction filtration or just a regular gravity filtration because we need to keep the solution hot. Otherwise, we are going to lose our main compound because they're gonna solidify. It's gonna be filtered off along with the charcoal. You have to maintain hot, solution hot. Okay? Makes sense, I hope.
Filter paper. Vacuum filtrations cool the solution too much and crystals are lost on the filter paper and funnel. Before filtering your solution, add some excess solvent and heat it to the boiling point to ensure that the compound stays dissolved during the filtration. Wet the filter paper with some hot solvent and filter the solution.
Okay. I modify this one in my grad school when I was a TA. We already changed this one, made it better than this MIT lesson. What we did and what I am doing at your college is making setup better to keep everything hot. Do you really think you have a coffee filter and pour the hot water will make this whole thing hot? I don't think so, right? It's gonna get cooled down instantly. Not hot enough. It may be just still warm, but you have to have a boiling going on to dissolve your crystal, right? That's the step 2 we've done. So as soon as you have, hot liquid dripped over the paper is still gonna cool down quick. And then you may see as you pour liquid is not gonna go down so quick. It will remain on top of the paper for a while as it loses heat energy. Then you are gonna have some crystallization of your compound which will be filtered off. That's a disaster. We want your compound go through the filter paper without color. So bottom here is supposed to be your compound and the pure solvent. That will be subject to the next stage, cooling stage, recrystallization stage. We don't want any crystal filtered off by cooled off, by delaying filtering, right? So what we do is we put this whole setup on our test. You cannot show this drawing as an answer for hot filtration. You must have, are you making note with the colored pens on your notebook? When I check your notebook, I'll see how many of you were actually doing what I asked and emphasized. This hot filtration is wrong. I mean, not as effective. You have a hot filtration with a hot plate underneath. You are gently warming, boiling this liquid, rising and rising hot vapors, warming up this funnel. That way you keep the whole setup hot. Okay? Then no matter how long it takes for these liquid you pour over drips, it doesn't matter. It is really hot. Hopefully you got that. I'm moving on.
Rinse the flask 2 or 3 times with hot solvent, filtering each rinse.
Okay, she's washing the flask or sometimes the paper with an extra hot solution because you see crystal actually crystallizing. That's not good, okay? And you know why. If you have a more liquid, the solubility increase when you cool down. Here, when you cool down with a more liquid, you're not getting as much yield because more liquid means more solubility, so you lose some main compound. This vaccine, how expensive it is originally? 1 microgram is how much? Hundreds of dollars, okay? Think about it. It's a lot of loss. If you are working for companies, directors are not going to be very happy for you lose every time you make something, you are losing significant amount of precious compound. I told you from this lab, this course, you guys are doing real science. Whatever you major you are doing. These are real now.
Finally, rinse the filter paper with hot solvent to minimize product loss. Crystals frequently form in the filtrate during the filtration, but they easily redissolve with heating.
Caution: your compound is no longer dissolved in a minimum amount of solvent.
Before proceeding to the next step, you need to boil away the excess solvent. Remember to add a few boiling stones to the solution and boil until solid begins to form.
You see what they did? That's why this is MIT maybe. She used the extra liquid I criticized, but they boiled it off. Okay? What's not so good? What if your compound is like a protein, DNA, very sensitive to the heat, and you're boiling it? Okay, it's like you caused the trouble and you are trying to solve it. It's better than not doing it, but it's a best you control not causing this problem. Okay, the problematic step here, boiling, is not always safe. It's a safe because this is just organic compound. Another minor defense of them is, you know, uh, in practical situation, you should be really careful, like I am teaching you. But this lab, the chemicals acting almost ideal, so they're not going to be dissolved a lot into the small amount of excessive liquid. But my position, I cannot just teach you assuming that you're going to just repeat this experiment in your company, in your hospital, right? You don't always do that. I have to make you prepare for unknown events coming to the humanity, and you'll be working there somewhere together. So yeah, I am trying to give you the best, but they have their own ways of reducing risk.
At this point, add a small amount of hot solvent to redissolve the solid. When your sample is once again dissolved in the minimum amount of solvent, set it aside to cool.
Even when you are cooling, pay attention. They're not cooling in the ice bath. Okay, this is not Gen Chem. Cooling doesn't mean ice bath. There's a very delicate process about crystallization. In the first human history, when they got the DNA X-ray picture, it was done by crystal. Crystallization is not just making some solid. Solid is not crystal. Crystal is a special. Okay, we're not there yet to discuss about crystal. Solid is not crystal. When I look at your outcome, I know you made a solid or you made a crystal. The people, the group who made just a solid, is the one that did not listen to me, put the product into the ice bath right away so they can form crystal quickly. Always remember, rushing is causing trouble. You have to take enough amount of time. Okay, the details hopefully we can discuss today some point. Let's see. So slowly they're cooling it for very good scientific reason.
Cover the flask to prevent contamination with airborne.
Okay, to cover is not to have a vapor not able to evaporate. Okay, it's a gas. Gas is evaporating anyway with a cover. Don't forget the covering with the paper or glassware or whatever. It's not preventing evaporation. It's to prevent something falling into it as an impurity. Okay.
Particles and allow it to cool to room temperature undisturbed. The flask can also be placed in a beaker stuffed with a paper towel to slow down the cooling.
See, even slowing down cooling with the insulation. That's MIT method. That's what we do in your college lab as well when I teach.
And promote slow crystal growth. This is especially helpful in a cold laboratory.
You see what she did? She had a paper on the table and she did not flip it, right? She put the side that touched the table over it. Oh my God, right? She should have flipped it.
Ideally, crystals will begin to form as the solution cools. You may want to watch. It can be very beautiful.
It's beautiful. Yes, I agree. I can imagine those little molecules coming near the crystal and finding best positions and feeling most attractions and stabilization and get stack up and keep repeating this come into the feather looking
If the solution reaches room
crystal.
temperature without crystal growth, you may want to try a trick or two to jumpstart the process.
Yep. The following portion of the video is when you don't get the crystal or not enough crystal. You know how much you added. Then you should know how much roughly you expect. I got the crystal, but it's not as much as you thought you would, right? Then you do the following tricks.
First, try scratching the side or bottom of the flask with a glass rod. Don't press too hard or you'll break it. If that doesn't work,
so that is making the glass is a silicon oxide polymer, okay? The OHs are on the surface. Literally, the surface of the glass is all hydrophilic OH functional groups there. So without disturbing, these OHs are interacting each other and having their own most stable orientation naturally. But we want to break those bonds and make the OH attractive for things in the solution, not OHs of glasswares themselves. Okay, we're disturbing them, like brushing. Then the OH is going to break their own interactions of the glassware molecules, and then it's going to stick out for solution. Then the strong partial charges of OHs on the glass is going to attract some of the hesitant crystal molecules, promoting stacking up. Okay? Again, what I'm saying is not something you hear and then just forget. This is the level you want to put on your answer sheets on the exam. the molecular description, the invisible thing you describe as if you see it. Okay, that's a grade answer. Like I said in the first day, explaining the syllabus.
Try adding the seed crystal that you set aside at the beginning.
Yeah, now here it comes, why you saved it, just in case. The crystal is mainly the main compound, right? So they are already stacking things up naturally the way they would do. So as you put in, the solution is saturated because you cool down, you have a minimum solvent. So the crystals are there, saturated, almost coming out, but they're not. You just need to attract them in the right manner. So you put your crystal there, showing like a, hey, look at me. I have this shape of an empty space available for us. The same guy, you, not the impurity, but you, the right guy. I have a right shape of a room made for you. It fits you. Just come and sit down. It's nicely, snugly sitting and making it happy. Then that makes another surface ready for another same molecule, the pure guys, not impurity. The impurity have a different shape. It's not gonna fit there. That's why the crystal seed of same compound, not any crystal seed, will help. You need to know how to explain these things for our test. Simply seeding, scratching, whatever, it doesn't, earn more than 5 out of 10. Okay, I'm keep saying this. You should be alert and get ready. Learn right way, understanding, imaginative, creative way.
If you forgot to set aside a seed crystal,
You are
you can also
making,
try dipping a
yeah, you are making crystal. Okay, the way they do here is you are making crystal out of the crystal solution here. So it's like second version of the crystal seed addition.
glass rod in the solution, letting it dry so that the minute crystals form on the surface, and then dipping it back in.
You may do a few more times, not just the once. Okay, dip it, dry, dipping it. Don't shake it. If you shake it, you might end it up redissolving the crystal you just formed on the tip. Gently, without disturbing them, put it in the solution. Try to attract some molecules of solute, not solvent, and then take it out, let it dry. Now you have a larger uh, crystal seed. Maybe it's invisible, but it's there. Then you put it in gently and take it out, and you repeat few times. It doesn't have to be a visible crystal. It's still able to cause crystallization. But you have to leave the crystal on the tip in the solution, so that's why she has the glass rod still stuck in the Erlenmeyer flask.
When crystallization has begun and your flask is at room temperature, place it in an ice bath to drive the crystallization to completion. Leave it in the ice bath for at least 15 minutes before collecting the crystals. The final
Okay, you're gonna put it in the ice bath anyway, right? But why would you not put it in the ice bath from the beginning? Okay, you wonder. So hopefully we discuss it later. Um, but let's focus on these 5 steps of experiment. So we went through the very key 2 steps, including other steps. Now we reach the final stage. Especially washing is very critical. Let's see they teach that point.
Step in a recrystallization is collecting and washing the purified crystals. To do this, you will need a flask of ice-cold solvent, ethanol in this case, and a vacuum filtration setup. Always use a clean, dry flask to collect the filtrate. In many cases, a second batch of crystals can be obtained by concentrating the mother liquor and crystallizing a second time. Turn the vacuum on and wet the filter paper with a small amount of cold solvent.
The reason for you to wet the paper first is because paper, when it's dry, they're always making little gaps between the paper and the bottom of this inside of flask. Um, Also, the right size of the paper is the paper that sits inside without touching the wall, meaning it has to be exactly right diameter or it should be a little smaller, but it must cover all the holes here. There are many bunch of holes here, the floor of the inside. Okay, if you use a little bigger one, you have to bend and fold, then it's not gonna do good job. And also, because we have to do it later, many of them, I'll tell you one thing about this vacuum filtration. Vacuum filtration is causing a vacuum underneath. When it's a vacuum, boiling point of the liquid down here is get lowered. Okay, so evaporation is gonna taking place, meaning it's mini boiling going on. You're losing solvent. So whenever you have a mixture where you keep liquid as your final product, you don't want the vacuum filtration because with the reason I just explained, you're going to lose your product. Then when do you use this filtration? When we keep the solid as our main compound. Then it doesn't matter you lose liquid or not. And then you want to lose liquid as soon as possible because you got the maximum solid out of liquid by cooling. But these things are not cold, like a reverse of the hot filtration, right? So as soon as you pour the cold one over here, the liquid will take time to drain down and then it's gonna warm up. Then some of your crystal will dissolve. Then you're losing some amount of your crystal, ended up lowering your yield. Okay, so you do it quickly and you use vacuum properly and run vacuum first, have a vacuum ready to run and suck it out, right? Then you pour everything quickly and minimize time for liquid staying here. As you add additional liquid, don't do it when you have a liquid remaining there. Let all the liquid gone and then you add fresh cold liquid again so it doesn't dissolve away your compound at the low temperature. Every single action you do scientifically, there is reason planned out. Okay, you need to understand those things. Focus on those justification, the principles behind each every step of experiment.
Pour the crystals and the mother liquor onto the funnel using cold solvent to transfer all of the crystals from the flask.
Yeah, as you can see, she used small portions of cold liquid, not collecting them up, right? A little bit of it and pour out, a little bit of additional liquid and pour out, not many squirts at the same time. That's the exact thing I just explained.
Use cold solvent to wash the crystals and pull air through them to begin the drying process. After pulling air through the crystals for a few minutes, scrape the crystals onto a weighing dish and spread them out to facilitate drying. Depending on the compound, the crystals can be dried in a desiccator, an oven, or on a vacuum line.
I hope you noticed shining flakes, like a small piece of a mirror, okay? That's the indication of the small crystal molecules lined up very nicely and uniform manner and deflecting the light nicely and organized manner. That's the one unique behavior of the crystal. If you have a solid that's not crystal, it's not gonna be spiky, sparkling. Okay, it's not gonna be sparkling. It just um, scatter the light if it's solid, not diffracting. So diffraction is unique. Okay, make a note. Diffraction is a unique behavior of crystal, different from just regular solid. They're gonna be doing two
When one
solvent
ideal
system.
solvent can
Okay, I'm just gonna play away. I'm not gonna pause and explain because we're not doing it at your college, but just listen to them.
not be found for a crystallization, it is possible to use a mixture of two solvents. Once again, you must choose the solvents very carefully. In the first solvent, solvent 1, your sample should be soluble even at room temperature. And in the second solvent, solvent 2, your sample must remain insoluble even at the boiling point. The two solvents must also be miscible at all ratios so that they don't separate out into different layers during the recrystallization.
Okay,
We know from
at least the one thing I have to say, why do you even consider this thing, right? Okay, so you do crystallization in your professional lab to purify some compound into the 99.99% purity. I think crystallization is the only method out of all the methods you have seen or you will be seeing that can give you that purity. Okay. 99.99% pure thing we can take as a medicine, that kind of thing. Okay, something you put on the baby's skin. Okay, anything that goes into diaper of the baby, that kind of stuff. 99.99% pure. It has to be recrystallized. That's the technique. But we have only a few, common organic solvents with a different polarity, and you test out every single one of them. And some compound, they're not behaving proper way. You cannot do crystallization, and you need to do it. That's when you think of it. Oh, yeah, I heard about those things in that tough guy. Whose name? The Asian guy? Dr. Lee? Yeah, yeah. That guy said something about like mix the thing. That's enough. Okay, that's enough. Oh yeah, there was a way when this doesn't work. There is a method. Okay, that's enough. So they're using soluble one and insoluble solvent. It's not same thing. And then they mix them up, and then they are doing much better job than single solvent system. That's what they're saying. Just listen out.
our solubility test that naphthalene is soluble in both toluene and acetone even at room temperature. So which one should we choose to be our solvent 1? That depends entirely on our choice for solvent 2. We know from our solubility tests that naphthalene is soluble in water even at the boiling point. That makes water a very good candidate for solvent 2. While acetone and water are miscible, toluene and water are not. The recrystallization of naphthalene will be carried out using acetone as solvent 1 and water as solvent 2. As before, dissolve your sample in the minimal amount of hot solvent, in this case solvent 1, acetone. Add just enough hot solvent to obtain a clear solution. Then add solvent 2, in this case water, dropwise, until the solution turns cloudy. Swirl and heat the solution to make sure that the cloudiness persists. And do not confuse cloudiness with the turbidity that is observed upon mixing two solvents together. Once you have obtained a persistently cloudy solution, add hot solvent 1 dropwise until the solution just turns clear. Now you're ready to set the solution aside to cool. Once the crystallization is complete, cool down a mixture of solvents in a ratio similar to that which you recrystallized from. This cold mixture will be used to collect and wash your crystals.
Okay, just a 17-minute video for us is enough. I spent about 90 minutes for 15-minute video. Okay, I hope I put enough of a practical side of teaching. Feel like you are in the real lab. How do you feel? You feel like you're learning some practical things? Yeah, and you realize that our teaching at your college is not worse than MIT one, right? You know how much they pay my teaching? It's because I care about you guys. After getting job, do you want to feel like I don't know much? Whatever job you have, don't you want to feel like I know stuff? People respect you. Oh, this person really knows stuff, you know? When you compete with the people from other colleges, especially big name colleges, they know a little more, just like things you have seen. Oh, the director of this research institution, they give you this task for, this group and that group. And then one group, there was a guy who know this little more, you know. Then they solve it. So what I want to do is, like I said, yeah, honestly, we don't actually do it like they do in MIT Columbia, right? But I teach you like there is a such thing. Okay, okay. Today I have to do this. I don't know how to do it, but I know there is a such a thing. If you don't know there's a such thing, you don't even look for it, right? Then you can sit down and look it up, and then you can just do it. So that at least that much, if you put effort down the road, you can compete with them. Okay, that much I want to make my kids, my students, you guys, compete with the people who went to that big place paying big money. Anyway, let's start setting up for our presentation. This way, you guys understand presentation really well. If there's anything you don't understand, you have to ask them. Okay? Because in the real lab, you have to, after the presentation, right? I'll just say, let's do it. Then you have to actually go and do it. Okay? Grab the glass and then go to the balance area, and you have to actually do something. I'm not going to be standing there and telling you, okay, step one, this, step two, that. Okay, you're not even following the procedure in the textbook. Like I said in the beginning, inspired by someone's question. We're not following textbook procedure. Move the slide. Yeah, here we go.
Okay.
Okay. Yeah.
Um, Compound B is insoluble in wide ranges of temperature. So basically, that means that at room temperature and at boiling point, compound B is still soluble regardless, and that would not be what we want in this experiment because we want to find something, as we said, that's insoluble at room temperature but soluble at boiling point. So if you look at, I'm going to skip compound A because that's obviously, and go to compound C, you can see that compound C is completely insoluble at room temperature and boiling point. So that also would be an issue for what we want to use in this experiment. And then if you look at compound A is partially insoluble at room temperature, but then becomes soluble no, it's soluble at room temperature and then becomes insoluble at boiling point, which makes it a good solvent. So, and if you could kind of, I don't know if everyone remembers what we used, but I wrote it down. So instead, if we could think of compound B as the water, no, we could think of compound B as compound C as the water that we just viewed in the video, and then we can think of compound B as the acetone and toluene, which were
Excuse me. I need to correct the mistakes, though. I don't want to bother, but
is a
compound A, B, and C, they're not solvent. They are solid.
oh
You
yeah, I'm
are
sorry.
dissolving, yeah, you are dissolving A, B, and C in hexane. The hexane is the solvent. In the bottom of the screen, right, you see in hexane. The
Yeah, I know.
whole Yeah, solids are in the hexane, and C is not dissolving into hexane at all. And A is like you are saying at room temperature it doesn't, but at the boiling of hexane, the compound A is dissolving, so it is our main compound. Compound C is never dissolving, that's something we are removing from hot filtration. And the A is dissolving well, like you said, from the beginning into the hexane. So it's not good because a good solvent. If the hexane is a good solvent for this mixture, then compound B is not good in this hexane. Hexane is not good solvent for compound B because it is soluble even at the room temperature. So you don't want to choose a hexane for compound B. Compound A, whatever it is good in the hexane. So hexane is a good solvent for compound A purification with the impurity in it. Okay?
Yeah. Yeah.
Okay, go ahead.
And that's why I was kind of saying, like, instead of like paying attention to hexane, I wanted to refer back to the video that we were using, which that's why I said kind of just ignore that that's there. And imagine those being like the instead compound A would be like the naphthalene with ethanol. And that is how we
Mhm.
basically found that in the video being the good solvent. So that's
Yeah,
what I
you're
was
right.
trying to, yeah, I was trying to
Okay.
like switch it around.
Okay, I understand. Yeah, go ahead.
Okay. So can you see that I changed it or no?
Nope, I don't see any change. Now I see.
Okay. I don't know why it does that. But so these are some of the general like materials that will be used in this experiment. So we just have the ice bath, which is used to aid in the crystallization process because we know that the ice bath helps promote a better and bigger crystal growth. We have the Buchner funnel, which is used for pressure assisted infiltration. The Erlenmeyer flask used to mix the compound, which is being used in the beginning of the experiments. The vacuum filter, which will be used to help aid in the assistance of collecting the desired solid or the crystals. And the hot plate used to heat the solvent, and the filter paper, of course, used to separate
the solvent from the crystal. So now I believe my partner is gonna do uh, these parts. Of course, these are the known samples that we got, and I kind of tried to include a little picture here of what it
Wow,
looks like. Yeah,
beautiful.
kind of,
Yeah.
yeah, nice, kind of nice. Yeah, and then we have the our known samples here. So
Okay. If you don't see this slide, guys, because I have both computers showing this, maybe you need to refresh it, refresh the browser.
okay,
Go ahead. Yeah.
okay. So my partner is gonna do this part.
Hello everyone, I'm Simran. And first thing I want to mention is that please excuse the background noise because I live near a busy street. Okay, then I'll take over from here. As we all know, recrystallization is a powerful method to purify solid and crystals. Here's the procedure for recrystallization. The very first step is choosing an appropriate solvent. It could be one or more solvents, and it depends on the solubility of the given sample. It is important to put enough solvent to get enough crystals.
Okay, just a second.
Yes.
Because it's a problematic, only the time I intercept is, if there's a chance of, misgiving, misinformation or something like that. So here, it could be right, it could be wrong. So I want to make sure. Can you clarify what do you mean? Because it sounds like you can have a lot of solvent, but it's the completely opposite of what we actually aim to. So can you be more specific about this second item? Put enough solvent to get enough crystal. I don't know what that means clearly.
Well, just give me a second.
I can help with
Yeah,
that.
please.
Sure, go ahead.
Um,
Yeah,
so yeah, as far as the crystals, we never want to put too much of the solvent
Yes.
because
right.
then
Yeah.
we wouldn't actually be able to grasp the experiment. So we just add a little bit as we're going, and we like to stir it to see it dissolve. So you're just adding as you
It has to be the right proportion.
yes,
Yeah, so maybe you missed the one word. I don't know. Put just enough, right? Just
Yes.
enough solvent. That's what you meant, maybe.
Yeah, exactly.
Yeah, not enough solvent, right? Just barely enough to dissolve everything. Yeah, okay. Continue, please.
Yes. The sample is then heated until it starts boiling. After the second step, the filtration process, which is a method used in filtering solution that will crystallize, is performed to decolorize and remove remaining insoluble contam- contaminants from the sample. And then the sample is cooled down to the room temperature, and once it's cooled down to the room temperature, we put it in an ice bath to get the crystals. The last step is to collect the crystals and wash and dry them before doing any other measurements. Uh, Tatiana, can you please change the
yeah,
slide? Thanks.
yes. Sorry.
So here's the visual representation. Since we can't do it in a lab, we try to get this picture. In the first, you can see impure compound and solvents are being mixed together, and the temperature is raised by boiling it. And once the solute dissolves in solvent by heating, then the solution is cooled down to room temperature and then in an ice bath to get pure crystals of the solid form.
Okay, just a second. Again, let's make sure we don't confuse ourselves, right? In the previous video, there were 5 stages, but you don't really necessarily here showing same steps, right? The step one, you are not choosing right solvent, but you are already dissolving it. That's a step two in the video. So let's make sure everybody who are listening to this video, um, this slide is not showing the very first step. They are intending to show the experiment itself, not the testing for solubility, as a part of the step. But there should be, prior to this very first step on the slide, there should be one more step, as you all know, right? Also, the first step when you dissolve, the slide is giving little misconception as if you are pouring whole solvent at once. That's very, not true. Very, inaccurate method. As you all know, we are boiling the liquid, pure liquid, and then we are adding little by little to have just enough to dissolve, right? And also, when you cool down, there must be two stages of cooling down to the insulated environment to the close to room temperature first for the good growth of the crystal. Then you accelerate the last crystallization by putting in very cold environment. Okay, so there's a little difference. I just wanted to make sure you don't get confused. Okay, when
Oh,
you're
yeah.
done, you can move on. Yeah.
Since I mentioned the steps in a previous slide, so I thought this picture was close enough. So this is why I took that.
Okay. It
Okay.
has its own purpose. Yeah. I just want to make sure the listeners, clarify where these are fitting into our original lesson, 5 steps.
Yes. Yeah, here are some helpful definitions. The first one is boiling point, which is the temperature at which liquid boils and turns into vapor. Room temperature is a comfortable ambient temperature, which is 70 degrees Fahrenheit or 120 degrees Celsius. Solubility is an ability of liquid to dissolve, especially in water. Purification, removal of byproducts and impurities. And lastly, melting point, which is temperature at which solid is equilibrium with its liquid. We can go to the last slide. And finally, here are some useful tips. It is important that the solvent cools slowly. This promotes the formation of larger crystals. And if the solvent cools quickly, recapture the solvent could recapture the impurity, and you might not get better crystals. It is always important to choose a solvent that the impure compound has poor or low solubility at low temperatures, and vice versa, ensuring it will crystallize upon cooling and dissolve upon heating. Impurity must also remain its solubility at room temperature after experiment is complete. Using a glass rod to scratch the side of the flask increases glass surface area, which aids the crystallization process, and adds the appropriate amount of solvent. Too much could cause recrystallization. And as the video mentioned, organic contents are flammable, so never heat over an open flame. These are some references.
Yeah, so that's pretty much.
Yes, that's pretty much.
Okay.
You?
Well done. Well done. Um, you know, I think the students here will feel like, okay, the intensities and level of, standard I put in here is a little higher than what you presented. That's true. Okay. So am I disappointed? Not really. Well done. Why? I mean, the presentation, many students here may say, like, it's not there in your standard. True. My standard here is the standard you gotta reach some point in the semester before it ends. Okay, as soon as you reach there, the better grade you get. But in the beginning, okay, you guys are from Gen Chem. Gen Chem is what? They gave you everything, worksheets, every single stage. They show you what to do. Very pretty simple thing you need to do, and it's different Here you have to do everything. Lab notebook writings and managing whatever. In the lab, a lot of things are like flexible. Too many things to decide. Okay? You guys volunteer to present as a first goer. It's very daunting task. So always every semester I see something like this. It's not surprising. People who get A eventually can give somewhat, lower than standard I put, but that's fine. It's a beginning, and you show how hard it is to digest everything, and you only had how many days? Just couple days, right? Honestly. Now other people who will do in the future, they have weeks left. So I expect, better than you guys. I mean, it's not like you guys did bad, but since you are first timer, there are things you could have done better if you'd done it in the later time. That's why I'm saying good job. Good job. I've taught this course how many years? Nearly 20 years, guys. I didn't start my professor job last year. I've seen this thing over and over and over again. So I know. Don't worry, okay? Don't worry. I had thousands of kids in this course. I know where you are from. I know where you are right now. But most of all, I know some of you, how far you can go. Those people, I'll help you in this second video. It's the third time now of the day on the same subject.
My job is to make college easier because students.
That's enough for them.
Professor Dave here. Let's talk about recrystallization.
He knows a lot about the science stuff. Professor Dave explains.
After learning a variety of separation techniques, we will need to look at just one technique for the purification of solids. Sometimes a chemical reaction will occur such that a solid precipitate will form, which we can then filter out of solution. But it is inevitable that this solid will contain impurities. When the lattice structure is forming during the precipitation, ions and other particles that do not belong in the lattice will get trapped inside and disrupt the pattern of the lattice. There is a solution to this problem, and it is called recrystallization. So let's see how that works now. Let's say we have our impure solid that we wish to recrystallize. The way this works is that we will choose a very particular solvent in which to dissolve the solid. The solid must have a very low solubility in this solvent at room temperature, but a very high solubility in this solvent at very high temperatures, which makes sense given that solubilities will tend to increase as temperature increases, given the entropic favorability of dissolution. So we will choose a solvent carefully, and we will heat it up to boiling or near boiling. This will then be added to the impure solid, which has been placed in a beaker. We add more solvent, heating and stirring the contents of the beaker as necessary until all of the solid is dissolved, being sure to add only as much as is necessary for dissolution to occur.
You see, his explanation is pretty good, right? He explained the way it should be. Gradual additions and everything he said. Even he mentioned entropical process about heating. Okay, but this person's a really good teacher, Professor Dave. I think he is from Georgia or something. I forgot already. Yeah, he's good. So I recommend you to check on his videos. Not only this one. Okay, I will take few of them from his webpage. If you go there, make sure you like them, thumbs up, and subscribe for him, so he can make a more good video. All right, he's pretty good. Yeah, yeah. When you watch a similar video on the same topic from different person, you are learning different perspective or different way of connecting things. It helps. That's what I do when I study philosophy for myself. Okay, I am restudying philosophy and theology myself, and I am watching various videos from different universities just to make sure my perspective is double checked, triple checked, and so on. Anyway, so yeah, uh, this is a repeat of what we have learned, but see, your understanding so far makes you follow him better than when you were watching first time or when you were listening to our speakers today.
At this point, the impurities which were locked in the lattice are liberated and can now float around in solution. Once dissolution is complete, we can then begin the cooling process. This will be done by first removing any heat source and allowing the beaker to come down to room temperature. Then the beaker can be placed in an ice bath, whereby the cooler surroundings will draw heat away from the contents of the beaker. Crystals should begin to form in the beaker, which will be a much purer version of the solid, with the impurities having been removed, and which now are extremely dilute in solution. If crystal formation is slow or difficult to initiate, we can use a seed crystal, whereby we add a little bit of the solid that is supposed to form, which provides a surface around which ions in solution can coordinate, and this will kickstart the crystallization process. This can also sometimes be done simply by scratching the side of the beaker with a stirring rod, as this will liberate a tiny amount of glass that can also provide seeding behavior.
Okay, extra point chance. First two first people typing answer. What did I say earlier in earlier video? For the reasons. The scratching helps. How the scratching helps forming crystal. This can be midterm. No, type it please. This could be midterm question. I told you, right? We are going through everything quickly thanks to the Professor Dave, summarizing different perspective and organizing better, but let's see you understood. Yeah. Okay, 10 more seconds. 10, 9. Wrong is okay. I'm not gonna deduct point, okay? It's just the extra point I'm aiming to give. 1 point to the midterm. 9, 8, 7, 5, 6, 5, 4, 3, 2, 1. Done. Okay, that's it. No more. Let's see who can get some. I can give you 1 point. To form crystal faster, I mean, every technique we learn here is for, learning, forming crystal faster. Better result, yes. Fast process, yes, but it's not good explanation. If this was a test answer, then I'll probably get 7 or 6 point out of 10. Okay, all the other answers maybe 2 point, 3 points out of 10. Okay, that's how I'm gonna grade. So this is not time wasting. You are getting sense of how I'm going to make a question, what type, what kind, how he's gonna grade. Okay, But because this is an extra point activity, Tatiana, you will get 1 point. So these OHs of the glass, they are bound to each other at normal conditions. As you scratch, you break the hydrogen bond present on the surface of glass. Then they are free from each other, and now they're attracting other things using their partial positive and negative charge. They can form hydrogen bond, right? So some of the crystals reluctant to form crystal that are present in the solution, they are motivated by attractive force from OHs of their partial positive charge, strong charge, hydrogen bond amount of charge. So they can get pulled and start stacking up to the solid. Okay, that's how I said. And at least a few of you, again, was paying attention and find the value, the things that I said, and you were listening to me. Thank you.
Once crystallization is complete, we can use some filter paper on a Buchner funnel and dump the contents of the beaker onto the filter paper. Utilizing a vacuum, the solvent comes through the funnel and the crystals will sit on top, slowly drying, and after sufficient time, we should have crystals that are nice and dry and pure. We can test their purity by performing melting point analysis.
This part we do in the separate class, okay? So let's skip it. That's enough. Okay, now let me share this computer screen of my TA's computer screen. There. Okay, let's have a 10-minute break. We're back. I have a red sign for my connection. Do you hear? Do you hear me? Anything? Anything?
Yes.
Are you guys there? Okay, that's cool. Yeah, I still have a red sign for my connection, but luckily I have this TA computer. So let's see. I'm gonna make this one always visible so I know that you guys are still able to see what's going on. Okay, that's good enough amount. You see things. All right. I just put the extra point on your gradings, and I find there are 5 students already got 1 point. 1, 2, 3, 4, 5. Yeah, 5 students got 1 point. Good. Extra point. Here. So, skipping finding good solvent, right? Basically, as you know, recrystallization by now, after choosing good solvent, you want to remove this impurity surrounded by other main crystal, right? The role of the solvent is making this crystal lattice. You understand the word, crystal lattice, break apart. And you have now all of the solid molecules separated, including impurity. Okay? Then go through some steps. At the end, we cool down. We want only these guys themselves come back, leaving this guy alone. Okay? So how do you do that? That's when you need couple of factors. Let's talk about solubility factors first, then two-step two-step cooling. Okay? So solubility, we can go quick because we already talked about. Okay, our presenters, the speakers told us today. We chose the solvent. Okay, solvent already is chosen to have the impurity have a good solubility, like compound B in our one of the slides in our speakers today, like a compound B. Even at the low temperature, at the boiling point, the solubility is good. What if it's not good all the time? We remove the it through what process? Remove the insoluble impurity? Anyone? Hot filtration. Okay? Hot filtration removes this. I said this twice while I was going over. Yeah. So our impurity will be something like that. Then our main compound will be something like this. It wasn't soluble, but at the boiling point they dissolve better. Okay? But when you cool down, what happens? They come back as a solid because they lose solubility. But this impurity stay dissolved. Okay? But this can be dissolved and remain in the solution only because we went through complete dissolution. We completely broke the crystal lattice and liberated this impurity captured in the middle of the crystal. Okay? So solubility is key. So hopefully now you connect already given things in this perspective. Why we talked about solubility? To choose a good solvent. But what sense? You know, all the things we have done is there, but here in this main moment, that's the moment you actually remove impurity. Next moment is this. Bring just them, not impurity. Why not? Impurity, why wouldn't impurity interact with another molecule? See, there must be a reason for it. Okay? So two-step cooling. That's why that MIT video was so careful in losing the heat slowly. Okay? Slowly. Two-step cooling. Slowly. So this goes like this. You have a compound, say, that looks like, oh my gosh, what's happening? Okay, here, my bad. The compound looks like this. Okay, that looks like this. And then impurity, say, the impurity looks like this. So you have a 90% of this and 10% of impurity in your solid. Okay? So when you get a piece of a little solid crystal, in there, if it's visible, right? It's a point some millimeter size. How big is one atom? It's a couple angstrom. Angstrom is how much? 10 to the negative 10 meter. And the particle you see is what? Millimeter. 10 to the negative 3 and it's a point zero something. So we can say 10 to the negative, say 5 at the most. If you go below 10 to the negative 6, it's a micrometer, right? The hair is one of the smallest thing you can see with the visible eye, like a dust particle. That's about a micrometer size, 10 micrometer, 50 micrometer, that kind of thing. If you go sub-micro, then it's a micro world. We don't see them, like a bacteria. They're pretty big. So the point I'm trying to make is how many molecules you have in these small particles. But in your sample, you have thousands of these particles, right? Each one of those thousands of particles, you have these guys. How many? They are 10 to the 10 size, and you have about 10 of them, right? So let's say overall size, very roughly speaking, 10 to the 9 meter. And in this particle, 10 to the 5. So the difference is about 10,000 times. So you have, roughly speaking, very, very roughly, okay, about 10,000 molecules here. They stacked up in the tiny particle. As a chemist, you gotta have that kind of sense. And they are stacked up, okay? So roughly speaking, this is a flat molecule, like a piece of paper. And you have another piece of paper. You stack up nicely, right? If you stack effectively, it becomes a book, your organic textbook. Unlike a one page of paper, right? The textbook is pretty strong, isn't it? It's not easy for you to rip it off, right? They stacked up. But this guy here is like little piece of paper with some spiky stuff, like hydrogens, right? Methyl groups, spiky hydrogens there. Say you have some of them in the middle of the stack, here and there. Then the stack here is not that stable. Okay? But if you are paper, you obviously prefer having another piece of paper stack up. That's the way you have a maximum interaction all over the place, most stable. You don't want this molecule having something with the spikes. Then the next stacking will be not as strong. So you have a bunch of spikes, okay, in on your table, for example. You have 10 of these, 90 of these papers, okay? You're going to try to go home quickly, and you have to all put them in the back and go home, right? If you quickly do it, you have no time to sort things out to be most stable. So you put, sometimes paper and this a needle stack, and then, another paper and stuff. Messy, okay? Not very stable if you rush. If you go slow, then you can even have to do this. Am I going to stack the paper this way? No, 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 no. Let's do it this way, right? You move pages around and find the best fit, most stable interaction this way. This way, if you are a molecule, you only have this much of an interaction, not as a stable. You all listening to me? You're awfully quiet compared to my other classes. Wonderful. Thank you for telling me. That makes me feel so much better. Okay. So in the solution means what? You have a majority of liquid solvent, but you have a somewhat bigger molecules, solute. In our case, they are, where is the colors? Colors. home dollars. Okay, here you have 90 rectangular paper molecule, right? 90 of them. We dissolved them, remember? The second step. And then you have the needle thingy, three-dimensional needle thing, that you will see this in organic lecture more frequently. And 10 of them, okay? That's the proportion we are talking about. And they were separated when it's heated. When you cool down, now they are attracting one another because heat is a kinetic energy. They had enough of a motion energy, so they were able to go away from each other, although they are attracting one another. They have a partial charges on the hydrogen, partial negative charges on the negative charges on the carbon because carbon is more electronegative and stuff. All of these compounds, they have a little bit of positive, little bit of negative, different parts of the compound. Naturally, they're attracting. But because their motion energy we give at the boiling, they just break intermolecular force and let them go away from each other and they got dissolved. But as soon as you start cooling it down under boiling point, the motion energy go down, now attractiveness take over, now they are big crunching time. They come back before they diffused away, like a big bang, right? They are come back. But if you take away energy too fast, what happens is this paper come toward this paper without having chance to like measure out how do I gonna get stacked up to be more stable. They have no time. They lost the energy for motion, so they just need to come together. Okay. Not only they don't have time to measure things up, they have a other guy in the middle, and they are also attracting. Forget about best way. They just attract and rushed. So everything's gonna be collapsed. And you are recapturing impurity and you're stacking with the impurity there is making crystal not as stable, but also what's the purpose of this experiment? Left, leaving this thing in the solution, right? But you recaptured it. So you have to do it very slow. Then when this paper come along, they run into this guy and try to match up and saying, oh, I'm not that stable with you. So this guy go and this guy come down more. Now they find another piece of paper and say they run into this way. But they still have a motion energy because we are slowing down, and cooling down slow enough, okay? So they don't like this. They still have a energy to turn, and find the perfect match. Then this is a very attractive, so they don't move away from this. This is a very stable. So they stay like this until the other piece of paper, the naphthalene molecule, come down and find the best fit, and then they stack up nicely. When you do it slowly, take away their motion, their freedom. Okay? So this is the second reason for successful purification. First, break things down. Leave the impurity in the solution. And then stack them up, pure stuff, together, giving enough time to grow. Last, but most important thing, after knowing fundamentals, this will be connected to your lecture later, but starts now, here. If we did experiment today, this lab runs up to 6 o'clock easily. We may stay longer than 6 o'clock, standing there whole day. Okay, use all the things we have talked about, all right? You have a lot of these guys in your solid with the impurity. Obviously, this partial negative oxygen is attracting the positive hydrogen. That's how they stack up here. Now this nonpolar ring, they attract each other. Then other molecules in the solid, you have a dysfunctional group again, and the attracting hydrogen, and so on. The ring have a stacking going on. And time to time you find impurity and stuff. Okay, forget that for now. Let's just zoom into this region where you have impurity and other benzoic acid going on. It's there, but out of that thousands of molecules in one little tiny dust particle that you are dealing with. Okay? When you test for best solution, because choosing right solvent is the key to this experiment. It's one of the two keys I told you, right? Solvent and the cooling. Okay? One of the two key elements. So, say you understood the cooling part, but how do you know which solvent is good for you? You test out. You test out. Okay? But how? Why do they work? How does it work? Why benzoic acid must be water to have a purification? The test question can be easily propose one of the best solvent for this compound. Then you need to know what I'm trying to say here. So when you start with a nonpolar solvent like a hexane, medium polarity ethyl acetate, polar solvent like a water. Why not hexane? Why not ethanol? Why not water, right? We all know why superficially, because they don't match two categories. Number one, not soluble in water, not soluble at room temperature. The second one, soluble at boiling, but they don't match because these two will dissolve your compound benzoic acid well at room temperature. Water did not dissolve, but when you boil it, it will dissolve. Why they change? It wasn't soluble, but why it becomes soluble? And then how do you know some compound will have a good solubility to some solvent or not? How do you know those things? Okay? Organic chemistry is focused on structure, and then the structure will give you idea about properties such as solubility, acidity, basicity, or substitution, elimination, addition type of a reaction properties. They're all predicted by structure. So here we have a structure. You all know, even from Gen Chem, these carbon hydrogens are hydrocarbon, very non-polar. Okay, non-polar. These are polar, right? Oxygens and hydrogens. These are polar. Let's see. How many atoms here? Carbon, 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 and hydrogens and hydrogens and hydrogens there. So you have 6 carbon, 5 hydrogen, 11 atoms, non-polar. How many are polar here? 1, 2, 3, 4. 4 are polar. So if you average out, right, really roughly speaking, this molecule can be more nonpolar, a lot more nonpolar but it has a little bit of a polarity, right? Out of 15, 10, 11. 11 out of 15 is nonpolar. 4 out of 15 atoms are polar. So you can say, okay, more than 2 times, almost 3 times nonpolar than polar. So yeah, 75% nonpolar, 25% ish polar. So look at that. Hexane, just the carbons and hydrogen, nonpolar. The hexane love this ring, so this can dissolve. Of course, these guys don't like hexane, but they are minority. So, unlike our civilized human society, they don't care about minority, right? The major force, like the nonpolar ring in the hexane, so they get dissolved. Therefore, we cannot use it to recrystallize the solid because exactly why? Because later dissolving is not a problem with the hexane for benzoic acid. You dissolve them, you broke them apart. That's one main goal. You have to break them apart. But we have to get it back. You cannot get the solid back because they are soluble. Because of this step, hexane's not good. You understand that now, right? Because of that step, not so good. So again, the exam question is not simply how do you find a good solvent? Dissolve, cool, not only that, explain. Then you have to know how to explain why hexane's not good in practical side. Okay? Keep telling you what I'm gonna put on the test. Every single lab I'm gonna tell you. So don't worry about what you expect on the test. Get prepared from the day one, which is today, because I am not hiding anything. Okay, then ethanol. Same manner we just did. Ethanol, you don't know maybe, so I'm showing you CH3, CH2, then OH. 7 atoms, nonpolar. Okay, 7 nonpolar, 2 polar, 7 out of 9 nonpolar, 2 out of 9, about 20 some percent, about same, right? 20 some percent polar. The rest nonpolar. So this polarity is quite similar to this. Therefore, ethanol loves this. This part easily dissolve into the OH, same polar group. And this nonpolar group easily loved by nonpolar ethyl group. So, same reason as a hexane, it's a better reason than hexane case. Ethanol is not good. Okay then. Water. Water's extremely polar. They hate majority, nonpolar, not soluble. Okay? Not soluble. But they become soluble when you heat up. Okay, so what's the role of the heat? What is the heat again? Let's go back. Heat is kinetic energy. When we heat things up, the thing become more kinetic, meaning more motional. So solid has no motion but vibration. They don't go anywhere. They just vibrate and dance a little bit. But when you heat up, the vibration energy is so vigorous, right? They break the bond. They break the bond here. If they break the bond good enough, they turn into liquid. That's called a melting. It's not dissolving, it's a melting. If you still have a hexane, right? As it melt, it interact with the hexane same manner we discussed, so it dissolves well. It dissolved anyway without heat, but the heat loosen up the solid, so you dissolve the solid better with the heating. Okay, same for ethanol. But water, for example, water don't like this guy, but with the heating, they don't hold, right? Not anymore. They don't hold each other. Therefore, water can just hold on to this, then they're fine because they don't hold each other, become solid. Okay? It's broken by heat. That's why water can dissolve this thing with heat. How do you feel? Do you feel good? I mean, you understand deep. Wow, that's how things working. Do you feel that way? Hopefully, one or two at least. If it's everybody, I'm gonna dance around here. So, here you have a naphthalene, right? Tell me what solvent is best for you. If you understand my lecture, you have a naphthalene, totally nonpolar. Will this dissolve into the water with the heat? The answer should be no. Why? Yes, you have a naphthalene. Yes, the heat is going to break them apart. That's a melting. Dissolving is when the solvent able to mix with this guy, having some interaction with that guy. But where is the polar group here? Even when it's melted, right, completely with a very high temperature, the water is not able to grab on them. We cannot mix with the water. They're free from each other, but they don't. That doesn't mean this will mix with the water. You know, say I broke up with my girlfriend doesn't mean I match up with any girls, right? We gotta have some attractiveness to each other, right? Same manner here. Yeah, the naphthalene maybe have some bad time with a girlfriend and broke up with the heat. Something heat up, right? And they broke up. Doesn't mean the naphthalene will match up with the water. There's no common attractiveness, so they don't dissolve. Naphthalene obviously will dissolve into something like this if this was your solvent. Hexanol, cyclohexanol, because you have a polarity, but it has a nonpolar stuff in the solvent molecule. So when they loosen up, even when they don't loosen up, this will like this enough. Okay? The naphthalene nonpolarity will like this molecule very much because only two atoms are polar, the rest are nonpolar. Here you have a 6 carbons, 2, 2, 2, 2, 2, 10 and 11 hydrogens. So 11 hydrogen plus 6 carbons, 17 nonpolar atoms. This is a lot of nonpolarity. So this will easily dissolved in this cyclohexanol solvent. Okay, so you can predict the solubilities depends on the heat, not by memory. Okay, using this rationale, and hopefully on the test your answer should be more like this explanation, not memorize the answer made up before exam, okay, by some smart people or tutor or somebody from YouTube giving some standard answer for a specific situation. You memorize it and you come on the test trying to write that down. When I'm asking about different molecule, it's not going to work because you're dealing with the other compound. It's not matching up with this situation. So please learn how to analyze a structure depends on their polarity, and using that, see you can predict the melting point, solubility, thus recrystallization process, and we have more chances for you to practice and exercise on that process of thinking. So by end of the semester, you will be master in predicting properties. Thus, using different properties, you will be able to separate all kinds of mixtures, including proteins in the electrophoresis or Stern blots or whatever techniques you use in biology and biochemistry and microbiology, whatever. Let's see. I think I'm done, but let's make sure. Yeah. Yes, I'm done. Any question? You too. Thank you.